I'd like to talk about perfectly sampling colorings, proper colorings in graphs. First, I'd like to mention that this work is joint with Vishesh Jain at Stanford and Mitab Zani at MIT. So to begin with, let's take a graph with maximum degree delta, and let's look at k colorings of this graph. So just to recall, a proper k coloring is a map chi from the vertex set to 1 through k, such that two adjacent vertices, u and v, do not have the same coloring, chi of u, chi of v. Unless that psi sub k be the number or the set, of proper k colorings. So it's a well-known theorem that if k is at least the max degree plus 1, then we have a proper coloring. This is Brooks's theorem. And the obvious greedy algorithm works to find such a coloring. In this talk, we're going to talk about efficiently, that is expected polynomial time in n and k, sampling k colorings exactly from the uniform distribution on psi sub k. This is a bit different from approximate sampling, which we will also discuss in some amount of detail. So to begin with, in order to think about sampling colorings of graphs, we look at the standard way of thinking about this and doing it, which is through the Glauber dynamics. So for a vertex, let's let n of v be its set of neighbors. We'll use the notation throughout. Given a current state coloring chi in psi sub k, we consider the following Markov chain with the following update step. We sample a uniformly random vertex from the graph, and we sample a uniformly random color. If the color is not in any of the colors of the neighborhood of that vertex, we update the color of that vertex to this new color. Otherwise, we do nothing. This produces a new valid coloring. And all the other colorings are kept the same. We then iterate this as a Markov chain. So it's easy to verify in the classical that these Glauber dynamics form an ergodic Markov chain for k at least delta plus 2. And it is easy to check that the uniform distribution is preserved under one of these Glauber updates, these steps, and therefore, we see that it in fact gives the uniform distribution on psi sub k as the stationary distribution of this ergodic chain. So to algorithmically sample approximately from this uniform distribution, one can simply start with some coloring, which you can find easily, and then just run Glauber updates. Of course, there's a question of how quickly this Markov chain mixes. We get a polynomial time algorithm if this Markov chain is going to mix in polynomial time. We can provide a bound for how long we have to run. So one could ask, is it true for all k at least delta plus 2? And this is unknown. And we'll discuss what the state of the art looks like. Starting with the following almost folklore observation, more than observation, really theorem, that for k greater than 3 delta, we have polynomial mixing of Glauber dynamics. The proof is morally as follows. We have to sort of show that any two colorings will over time sort of mix towards each other, that we can sort of couple them to get closer in some sense. So as sort of a simplest case, and you can actually bootstrap this, consider chi and chi prime, which differ at a single vertex, a single color at a single vertex. And we're going to couple them by evolving them using the same choice of vertex and color in the Glauber dynamics. So let's consider what happens to the Hamming distance between the colorings. If v is at least distance 2 away from v star, then the distance stays at 1. If v is a neighbor of v star, there are delta of those, then as long as the color C is not chi of v star or chi prime of v star, then whether the Glauber update succeeds or not will depend on the neighborhood of that vertex v, but it will not actually depend on what chi of v versus chi prime of v are equal to, because we sort of guaranteed that C was not one of those, and so that doesn't come into consideration. However, for those two potentially exceptional colors, there might be a problem, and that might increase the Hamming distance by 1. That gives 2 delta total pairs. On the other hand, when v is equal to v star, you're never going to increase the Hamming distance, and it actually decreases as long as C is not one of the neighborhood colors of chi, or equivalently of chi prime, since they have the same neighborhood colors. So there are at least k minus delta pairs which decrease the Hamming distance by 1. So in some sense, you have a positive drift towards 0 as long as, or towards 0 distance, as long as k minus delta is strictly greater than 2 delta. One can make this precise and rigorous using path coupling, machinery of path coupling due to Bubbly and Dyer. Now, how might one do better? Jerem showed that one can do better when k is greater than 2 delta by exhibiting a more clever coupling. So now suppose again we have the same setup, chi and chi prime differ at a single vertex, and let's suppose that the colors again are c chi and c chi prime. Now let's evolve them again using the Glauber dynamics with the same vertex, but we do something slightly different. So first off, if V is not in the neighborhood of V star, we do the same thing as before. Choose a uniform linear in the color, update. However, if we have a neighborhood vertex, then we couple the colors in a slightly different way. We mostly use the same color, but if chi samples the color C sub chi, then we make sure to use C sub chi prime for chi prime, their update. And similarly, if chi samples C chi prime, then we make sure to use C chi for chi. And that keeps the fact that marginally on a single coloring, we're performing a Glauber update. But in terms of the coupling, again, there are at least k minus delta pairs, which decrease the distance. Same analysis as before. But now there are only almost delta pairs, which decrease, that can increase the Hamming distance. The reason being that when before, in one of the delta neighbors, for any of these vertices, if I chose the color C chi or C chi prime, there might be a problem. Now, if I choose the vertex C chi prime, there might still be a problem at for chi. But if I choose C chi as C for chi, there's not going to be a problem because the update will fail. The update will fail because we have C chi. And similarly, the update will fail for chi prime since we coupled it to use C sub chi prime, which is the color of V star for chi prime. And so it'll also fail. So no update will be performed on either coloring. And so the Hamming distance will not increase. Before it might have increased, but now it definitely doesn't. And that halves the number of bad pairs. This pairing trick allows you to get positive drift for a better condition when k minus delta is strictly greater than delta. This result has since been improved. The seminal work of Vigoda showing k greater than 11/6 delta, which stood for a very long time until the results of Chen, Delcourt, Moitra, Perrinau, and Possel, which showed an epsilon gain. Better results are also known if you assume, say, a minimum girth condition, so the neighborhoods sort of look triangle-free or otherwise, and possibly minimum degree bounds. However, the running time of all of these algorithms blow up as the error tolerance or the total variation distance you want for this Markov chain goes to 0. Now let's talk about sampling exactly uniform colorings. The work of Huber shows that you can do it when k is greater than delta squared plus 2 delta with runtime quasi-linear. Gamarnik and Katz showed for k linear in delta, k greater than 2.78 delta, for triangle-free graphs, you could do it, but in n to the O of log k time. So for fixed k, you have a polynomial time algorithm, but that blows up as k is allowed to vary. Liu and Yin show a similar runtime for k greater than 2.58 delta, and now you don't need this triangle-free hypothesis. And finally, Liu, Sinclair, and Srivastava recently showed that for k at least 2 delta, one can do it with an n to the e to the poly k runtime. These numbers are quite large in terms of the exponents for any fixed k. Most recently, in a breakthrough work, Bhandari and Chakrabarty showed that for k greater than 3 delta, you can do it in quasi-linear time. Let's say delta is fixed. And this matches the Folklore bound for approximate sampling in terms of how quickly it can be done. So let's talk about how to do the Huber result and then how to improve that to get to Bhandari Chakrabarty as well as our results at the very end quickly. So first of all, what are our results? When k is at least 8/3 delta, we can now show quasi-linear as opposed to 3 delta. 3 delta was noted by Bhandari and Chakrabarty as sort of a natural barrier to their approaches in 2 separate places, and we provide improvements to both of those in order to break this barrier. And in fact, one can do a little bit better. One can actually improve to 8/3 minus epsilon. However, there is a barrier at 5 delta over 2, and see our paper for information about this epsilon improvement as well as how to see this barrier and understand it more broadly. One sort of final thing to note, which has been swept aside for a bit, for perfect sampling, it's sort of a tricky business because there's no room for error. So what happens is, for example, if I had to perfectly sample from the Boolean cube, that's very easy. I just independently do it in every coordinate. But for colorings, you have no such nice structure. So how do you do it? It turns out that in order to do it, one has to run some sort of modified Glauber dynamics along with a stopping criterion. And the stopping criterion is very complicated and could depend on what the coloring looks like at a certain given time and other things. So the actual running time here is instance dependent. But you have a good expected running time. And so one can show that you expect everything to behave very well, and it won't take too long to output. And in order to be a perfect sample, conditional on outputting something, that output is a uniform sample. It has the uniform distribution, which is different from the Markov chain approach where you sample, where you update for a fixed number of steps and have some but approximate distribution. So in order to do this, the stopping time idea, one uses the general procedure due to Prop and Wilson called coupling from the past. Given any pi on any finite state space sigma, one can actually do this in sort of an abstract framework. Let me describe it. What we do is we construct a very special distribution on the set of maps from sigma to itself, which satisfies the property that A, it preserves pi. So if I sample something from pi and I apply my random map to it, these are independent, then I get something, an output, which is still distributed like pi. And let's say that the probability that f is constant, this random function is constant, is at least 1/2. Then what we do is we sample random functions until we hit the first time, which is random, which we have the random function being a constant function. Then we take any input on the state space and we plug it through that constant function and then f negative t plus 1 and then ... up to f negative 1. You can see this sort of goes backwards, and that's why we negative index this. Why is this thing distributed exactly like pi? The reason is that with probability at least 1 minus 2 to the negative I, at least one of these functions, f negative 1 up to f negative I, is going to be the constant function. And if it is, then we can easily see that this evaluation, no matter what omega naught is going to equal the same as f negative 1 up to f negative I applied onto some independent sample of pi, just because we know that f negative I and f negative t are constant functions under this event, or there is some constant function between f negative 1 and f negative I under this event, and also f negative t we know is a constant function. And so it doesn't matter what happened further backwards in time. You can think of this as sort of taking a uniform sample and then running it through an infinite sequence of events, starting from the infinite far past in some sense, and providing you with a perfect sample at the end of time, or at the end of our thing as well. Of course, that doesn't actually make any sense. But the point is, since we guaranteed that we'd eventually reach a constant function when going backwards in time, I don't actually need to know what was inputted into that function at that point in time. So you can sort of think of this as coupling from the very far past in some real sense. Great. So to apply this to colorings, we need a random map on colorings with two properties. Those properties. What we'll do is we'll write it as sort of a composition of polynomial number, in some sense, Glauber updates, which are just some random functions, random maps, which when composed together give this big function. And we want it to have these properties. Each of these FIs, as I mentioned, will be Glauber dynamics, although the vertex might not necessarily always be uniform. However, which vertex you choose is not going to depend on the coloring. If it did, of course, that would make everything go awry. In doing so, this immediately sort of guarantees that we preserve the uniform distribution. The hard part is showing that this composition map is constant with high probability, or with at least a half probability. In fact, we even need to be able to give an efficient computational certificate that it's a constant function, with enough probability in order to run this argument. This is very non-trivial because our coloring space is exponential size. In order to control these functions and understand when they're constant, we use a method called the bounding chain method, developed by Huber as well as Hagstrom and Nelander independently. In order to check whether this function is constant, one might just compute these images over time of these composition functions. But of course, the problem is that the state space is exponentially large. So this is not going to cut it. Instead, one simply sort of finds a chain of bounding sets which look like a product set. So at every vertex, I have a list of colors, and let's somehow guarantee that after doing the ith collabor update, I can write down a list. I can write down sort of a computable list that might be random depending on some of the updates and such. But I can sort of write down like what fi, which random function it is. But doing it in such a way such that I know that the image after these I+1 compositions is within this product of lists. So it looks like a list coloring of this form. And then hopefully we have a positive drift of those lists randomly down towards size 1. And if all those lists are size 1, then we have a constant function, and we would conclude. So let me quickly describe Huber's sampler. Let's say the vertices are v1 through vn. At the beginning of time, the lists are all 1 through k. Then we go through the vertices in order, v1 up to vn, and we update its list to be a uniformly random set of size delta plus 1. And we also independently are going to sample a random ordering that we're going to use in order to define the actual update function f sub I later. But we'll be able to guarantee that the coloring has each color in one of these lists. Then for the remaining steps, we independently choose a vertex, or uniformly choose a vertex. And we uniformly choose a color CJ from the color set. Although for convenience, we remove the singleton set S sub j minus 1, which is precisely, you look at VJ, you look at its neighbors at the previous time step and what its bounding lists were. Some of those lists are size 1, which basically forces the coloring to have those colors in those elements of the neighborhood. Of course, we're never going to want to update our color to one of those colors at VJ. And so we might as well just ignore it, basically. And that's basically all that's doing. Now, there are two cases. If CJ is outside the union of these neighborhood lists, we know that recoloring to CJ is never going to cause a problem. And so we can say, OK, let's just recolor to CJ, and let's set the bounding list to see just a one element list CJ. We just know what it is in some sense. That is what the update is going to be when we get to this point. However, it might be in the union of lists, in which case it's unclear. Depending on which coloring we actually get, we might be able to update, we might not be able to update. So instead, we just decide not to try to do that at all. And instead, we just sort of sample a uniformly random list of size delta plus 1 and in some sense start over. Now let's very explicitly describe what these updates actually are. So these initial updates are as follows. I have my coloring and I'm running it through, and at some point I want to apply like fi. So I had already chosen this uniformly random list along with an ordering. What I do is I look at this vertex vi, I look at its neighbors, I look at what the coloring actually has as neighbors. And I look at the first element in this list of size delta plus 1, first in this ordering, random ordering, which is not in this neighborhood, and I recolor to that. So that preserves the property that the color is inside the list. And if you forget about the list and just look at what marginally happens on the coloring, one can easily say that each color that can validly be recolored is going to have an equal probability of being the recolor, because all of these random orderings, this random set is uniformly random. So it does perform a valid update, preserves the uniform distribution. Similarly, in these cases, what's happening is, okay, we sample this CJ uniformly. And if it's not in this union of lists, we just set it to be what it is. Everything's great. Otherwise, we attempt to perform, we just sort of start over and perform the type of update that I just mentioned earlier. And the point is, because of this uniformity here, one can easily check that sort of forgetting about the list and whatnot, you again will have some sort of uniformity in terms of the update, and it will work out. Now, the lists often are going to get smaller, but not always. And analysis shows that you have a positive drift towards the list size 1 as long as k is greater than delta plus the union of the list sizes of the neighbors. And this is a pretty general phenomenon for these types of algorithms. Since the list sizes are at most delta plus 1 after this pre-processing step from 1 through n, you see that when k is greater than around delta squared, you have a positive drift and the result will follow. Bhandari and Chakrabarty show how to ensure that this union of lists is always at most 2 delta. Or first they depress all the lists down to size 2, and then they show how to keep them at size 2 in some sense. And both of these things, the pre-processing as well as these updates, will require k greater than 3 delta in a hard way. The main idea behind their approach is to use a method of bias sampling. So they'll ensure that the list sizes are always 1 or 2. And that'll ensure this condition, for example. So I'll just describe how they do an update once, let's say, we already know that the list are size 1 and 2, how they perform the next update. So what they do is they choose a uniformly random color that is not in the union of the lists. And they choose a uniformly random color that is in the union of the lists. Let's say remove the singleton colors again, because we can always ignore them. With some appropriately chosen probability, they set the list to be size 1 and equal to this CJ. This CJ is always guaranteed to work in terms of if I want to apply my function, I can always potentially just recolor to CJ. It'll never mess it up. CJ prime is a little iffy. It depends on what coloring I actually have. The idea is with some probability, we let the list be size 1. With some probability, we let the list be both of these colors. And then when we actually once we actually have some coloring and we want to run it through this function, what we do is we look at CJ, we look at CJ prime, we look at what the lists actually look like, and we look at what the actual colors of the neighborhood actually are. And based on those, we then choose like CJ or CJ prime with certain new probabilities that depend on all this stuff, the coloring, everything else. And you choose these biases in a way that it perfectly lines up, such that if you forget about the list and everything, and you just look at what it marginally does, given all this information, what it marginally does on a single coloring in this neighborhood, you know what these lists are, and you know what the thing is, and you want to see how it recolors. One can actually choose these biases in a way that it averages out to uniformity over the possible recolors. This is an incredibly clever trick. And using this method, they can run it through and make sure the list sizes are always 1 or 2. And again, as mentioned, you also need to improve this initial pre-processing step in order to do better than 3 delta, because not only does this pre-processing step require 3 delta, but also this drift step requires 3 delta. So there are 2 places where one needs k greater than 3 delta. So let me just, with the time I have left, briefly describe what we do for both at a very high level. So in terms of the positive drift phenomenon, we use Jerram's trick at the level of bounding chains. So suppose that we look at the neighborhood and we have some lists and they're size 1 or 2, let's say we already know that. So either all of them are disjoint of size 2 and we have a union of size 2 delta, or there are some overlaps. Okay. If there are overlaps, then we're sort of winning in this condition, this union condition over here. But if there aren't overlaps, we have many disjoint pairs in this neighborhood. So let n star j minus 1 of v be those neighbors w of v, which have a pair which is disjoint from all the other lists. In this situation, with some probability, we let our list of size 2 for the vertex v that we're looking at, vj, literally be that list, that disjoint pair list of size 2. And the key point is that since this list of size 2, since those colors can only appear in the neighborhood at that one vertex, we cannot have both of those colors appear in the neighborhood. And so whichever one appears, we could always recolor V to be consistent with this list by just choosing the other color. So similar to Jerem's analysis, we have this sort of pairing of these colors that allows us to be more efficient. And then we do the bias sampling similar to Bandari Chakrabarty. And as it turns out, this allows us to have a singleton set with higher probability because we're doing some of this coupling or pairing in order to be more efficient. Again, there's a delicate balancing to have a uniform Glauber update. And as mentioned, either you have a lot of disjoint pairs, this first situation, or you have a lot of overlaps, in which case this union is small. And so there's sort of a win-win analysis that can go on here. That allows you to break this barrier. As for the pre-processing, I can describe the additional key element as follows. We look more closely at the structure of the graph. By using algorithmic low-loss local lemma, we can find a set which is around a third of the graph, such that every vertex, both in that set and outside that set, let's call this set S, a seed set S. Every vertex has around a third of its neighbors inside the seed set and 2/3 outside, let's say. Okay, now Bandari and Chakrabarty just immediately make the list size 2 in some sense, after some other stuff. But we instead make the list of size almost 3, which no longer requires k greater than 3 delta or whatever, but requires a weaker condition, which we can stomach. Then the list in the seed set, or the vertices in the seed set, their neighbors do not have like arbitrary lists anymore. They have lists, some of which are arbitrary, but some of which, around a third of the neighbors, delta over 3 of the neighbors, are in the seed set and have already been made to have lists of sizes 3. So you can imagine this depresses the situation in some sense and allows you to do more. You can make those lists of size 2. Finally, for the vertices outside the seed set, now they have around a third of their neighbors in the seed set, which have been made of size almost 2. So you can imagine, again, you might be able to gain something and say, okay, we can now make those vertices have lists of size almost 2. And all this can be performed as long as k is greater than 8/3 delta because of this extra information we have around the neighborhood instead of 3 delta. And again, one can actually make this 8/3 minus epsilon. So with these 2 extra ideas and ingredients, we can break these barriers and do better perfect sampling. That's all I have. Thank you for your attention.